this is an interesting thing, and so Michael's been working on this a lot, doing beautiful things. So it's going to be connected to what we just looked at. So it's a little excursion. Just to remind you again, cartograms. And there are, I think actually it's funny, like we've gotten to a version now where we have the, the square map, everything gets represented by a square, and that seems to be helping for a lot of the visualizations. It's been a really interesting transition, and maybe hexagons as well. So the 48 states plus Alaska and Hawaii will be these just squares, and that's reasonably, you can see it's the U.S. And for things like who voted for whom, and right, things that you don't necessarily want to have population showing, or more importantly, say the actual physical size of the state showing, because it's misrepresenting things, then they're much more powerful. So we've used them as well. They're very nice. But there's sort of been a long struggle in geography and cartography to represent things well. And so here's a game where you do diffusion based on something. So this is population, right? So you basically take the original map, then you sort of uniformly distribute a population, the actual population across that thing. Put in the oceans, you put in the average population for the whole map, if you like. We'll leave Antarctica alone, and then just let it diffuse, right? So India would start off as a bigger blob, and it's going to push out, and then and so on. So somewhere like Canada gets squeezed, right? It has a lower population than the oceans around it and the US in terms of density, so it's just going to get squished as things kind of move themselves around. Indonesia, it's a huge place. It's going to really expand. Australia's going to show how big it is. So these are still they're very distorting, but they keep the one thing they will do is keep the boundaries the same, right? So this border, that if that crossing there is the same as it was in the original one. But it's diffusion, random walks. It's very nice. Again, just going to pop through it. I showed you these things. So things like child mortality. These have been used. I mean, these have become somewhat powerful for people to, right? Spending on healthcare doesn't work. And you see Africa disappears in this case. HIV. So these are really, there's some potency to this. Okay. But the idea of this is, so I think this becomes a profound thing. So if you take that original map that we had from Gassner and Newman and then apply this diffusion to it, if you diffuse in the right way, then you see that all of these little shapes are about the same size, right? So it means that you've kind of figured out what the underlying balance of density of facilities is relative to population. And so, so this one is where we've equalized based on just population density. So we've let things diffuse. So these counties that were in the middle of, like the Rockies and some of the Midwest that don't have as many people in them, they're going to get squished. And these big, the coastal ones will spread out and become larger. But this ends up with a bit of a strange looking thing. I mean, the details aren't very easy to pick up, but it's not normalized properly. Whereas if you say, well, let's instead allocate to each little facility area the density of people there to the 2/3 and then let that diffuse, then that equalizes, right? It ends up being a nice thing. So the bigger story, and hopefully we're going to have some beautiful things to show eventually for this, is that there's this idea of equipartitioning, so that systems, complex systems of all kinds, end up being equally partitioned in some way, right? So the simplest, this is not a complex, but you've just got water in a container and it's going to end up being flat. You just leave it there, it'll flatten out, and so there's no, it's in equilibrium, right? And equilibrium is such a profound thing in natural phenomena. It's been a big driving piece in science as we quantify things and understand things. Like the gas in this room is sort of in equilibrium, kind of in a sense, like it's moving and so on, but it's not. And then we have this idea of many systems that if they get bumped away from it, they relax back to it. Many complex systems are, depart from that because they're driven, right, in some way. There's energy being pushed in and it's moving in some way and it's doing something interesting. But it seems even then that if you look at it in the right way, like the hot model, for example. So a hot model, we have this very uneven spread of these fire breaks around regions of forest. But if you calculate the risk, right, the risk, which is the probability times the amount of damage, right, so the big area out here, if you recall this, and I know I'm just making, right, the probability of a fire out here is very low, but the risk, you know, but the damage is really quite bad. So the risk is, you know, whatever it is. That actually, once this whole thing is kind of in equilibrium in a sense, is that the risk is evenly partitioned. So it seems like we should be able to kind of move up through sort of a series of arguments, away from something like just plain equilibrium where it's like an energy balance or something like that, to something, a system that's being tested, like evolutionary systems, engineered systems, that end up being balanced but in terms of, say, risk. I don't know, that seems like a really profound thing. We'll get to it.